Okay, this is RTI, and we are on FRQ Type 5 table questions. Probably my personal favorite of all the types. So things that are frequent with these, a lot of the information is presented in tables. We've looked at table types of problems throughout our calculus first semester kind of journey. Often includes like average rate of change, instantaneous rate of change, aka derivative, but for instantaneous, average value, we've been practicing that formula a lot, and then Riemann sums or trapezoids. Do you guys know how to use the regression tool in your graphing calculator at all, like linear regressions, quadratic regressions, like that stuff?
I believe so, but we can use a refresher.
Well, it's not allowed on the AP exam, so just don't use it. So if you don't know what it is, don't worry about it. I just want to if you have used the regression tool before, you can't use that. I've never shown it to you, but it's not technically allowed on the AP exam.
What is it?
It's just basically like, remember when you did like the ball bounce project in
So you plug in
LS2?
values.
You plug in values and it gives you like all the equations and stuff. That's not allowed on the AP exam. But we've never used it before, and there's no really need for it, but just that was like one other thing I thought of with the table type problem. You can't like use the table feature and get a regression from this. Okay, so the first one we're going to try is a no calculator one from 2015 exam. Joanna jogs along a straight path. For 0 to 40 for her time, Joanna's velocity is given by a differentiable function v. Selected values of her velocity, where t is measured in minutes and v of t is measured in meters per second, are given in the table. Use the data in the table above to estimate the value of v prime of 16. Okay, so obviously since I'm not given like an equation here, I can't find the derivative, I'm just given the table. So I'm just going to approximate v prime of 16. So here's what you have to show. You have to show the calculus. V prime of 16 by finding the average rate of change between 20 and 12. Okay? So we would do v of 20 minus v of 12. I feel like these are the ones that I had you guys do like that first week of calculus, and I was like, look, you're already doing problems from the AP exam, because we had been talking about like average rate of change and slope and kind of stuff like that. Now, since this is no calculator, we don't have to numerically do anything, but we can't leave our answer like this because we have to pull the values from the table. All right, so we just have to take this one step further. V of 20 is 240. V of 12 is 200. Okay, you could leave your answer like this. We should include units. It doesn't specify, but when in doubt, put units. And this one was only worth 1 point for the approximation, so this number. And this would be...
Lucy Kaplan, if you could report to the egg room, that would be awesome. Lucy Kaplan.
Velocities meters per minute, so this would be meters per minute or meters per minute squared. So you could do that. If you want to check your numbers here, that does simplify to 5. 1 point for that one. Okay, here's a good example. B says, using correct units, explain the meaning of this definite integral. Okay, anybody know what that absolute value of velocity means? Remember? Yes.
Distance traveled.
Total distance traveled. Good. And then they want us to approximate that value using a Wright-Riemann sum. Okay, so it says using the correct units. So we could say this definite integral, when I have the absolute value, that represents the total distance she traveled, so Joanna jogged. In meters.
Olivia Horsfall and Brandy Exley, if you could report to the egg room, that would be awesome. Olivia Horsfall and Brandy Exley.
Over the interval of 0 to 40 minutes. You should also specify that because that's where those bounds come into play in that definite integral. All right, so now they want me to actually evaluate this using a Wright-Riemann sum. Do you guys remember how to do these? I love Riemann sums. Okay. So I like to actually kind of like draw in little like intervals here. So I got to do a right Riemann sum between 0 and 12. So I have to write like my delta x or my change in x, or like my width of that rectangle above the table here. So we have here, my first one is 12. This one, the difference would be 8. This difference would be 4. This would be 16. If that width is constant, you can like factor it out and then just multiply by the sum of all the right-hand rectangles, like the outputs. But when it's not, we're going to have to set this up with separate rectangles. So because this is an approximation, I'm going to use that. And we got 12 times my right Riemann sum, I would use 200. Plus the next one, width of 8 right, I would use 240. Plus 4 times 220. We're doing the absolute value, so we wouldn't use negative 220. We use positive 220. That's just telling me what direction she's going in. Plus 16 times the right is 150. What would my units be here?
Quick question.
Yeah.
Would it be negative 220, or is it because of the absolute value?
Yep, because the absolute value wouldn't be. That's just telling you in what direction she's jogging.
Okay.
So we're trying to calculate the total distance traveled. Good question. If they would have asked me this, Dalton, to evaluate this, then I would accumulate the negative area in evaluating the plain old definite integral, but absolute value, we treat that as a positive. All right, what would my units be?
Meters.
Meters, good. So you could leave your answer like that. Just as a reference, you get this number. Okay. Part C says Bob is riding his bicycle along the same path. For 0 to 10 minutes, Bob's velocity is modeled by B of t. Okay, this time they're giving us an equation for Bob's velocity. T is measured in minutes. B of t is measured in meters per minute. Find Bob's acceleration at t equals 5. All right, well, we know if we're given velocity, we can find acceleration by taking the derivative of velocity, which that's a nice easy polynomial. We get 3t squared minus 12t. Okay, so all I need to find, they're technically using B. I should do this for correct notation, sorry. They're technically using B of t for his velocity. Okay, so the acceleration at 5, you just plug 5 in. Again, you can leave your answer like that now that we've done all the calculus and we've plugged in the numbers. What would my units be here? Just to be safe, let's put some units. Well, velocity is meters per minute, so meters per minute or meters per minute squared. That number ends up being 15 when you simplify it. But you do not have to. 2 points for that one. 1 for using the derivative b prime of t, and then 1 point for getting the right answer.
Was this like A?
Just like A. This one?
Yeah.
Yeah, kind of, except the difference here is we're getting an equation instead of a table. Yep. I thought when you first said A, you meant like acceleration. Not like part A. Then I got it. Okay, part D. Based on the model of B from part C, find Bob's average velocity over this interval. Oh boy, here we go. We know our average formula. I do have it written here like the generic. We do 1 over B minus A times the definite integral from A to B f of x dx. Okay. So for Bob's average velocity, We're going to do 1 over 10 minus 0 from 0 to 10. Bob's function. Now, since I don't have a calculator, I'm going to have to do this by hand. So I'm going to actually write in the function instead of writing b of t. If this was a calculator-friendly problem, I would just write b of t, and then I would use my calculator to crunch this number. I have to do this by hand. Here we go. It's 1/10. Good thing this is a nice, easy polynomial antiderivative.
Hayden Walker, please report to
1/4.
the Myers room. Hayden Walker.
1/4 t to the 4th minus 2t cubed plus 300t. Okay. Now, here is where we have to show the fundamental theorem of calculus. So we have to show this, plugging in our upper bound. Plugging in our lower bound. And then you can just leave your answer just like that. It feels so weird, doesn't it, to leave your answer like that? Yes, sir.
Could you just do -0?
In this case, you could, yeah. You could do -0. Yep. You can do -0 here. Good question. Just be careful with that in case it's something that doesn't cancel out to 0. This would be meters per minute, his average velocity. Look for like those keywords and let the units kind of help you. For reference, we did get 350, but again, you will not be expected to compute that. Leave it just like this. Okay. Next one, we're going to look for the 2008, and I feel like there's kind of a weird question on this one, so I want to go over it together. Oh yeah, and this one is a calculator-friendly one, so this would be a good one to do. So while you're getting out your calculators, let me pull up mine on my smartboard here. There's the square guidelines for the problem I just did. Okay, so the only one you really need your calculator for is part B. Okay. So, reading through this one quick. Concert tickets went on sale at noon equals 0 and were sold out within 9 hours. Okay, this one's a little different. This time they're giving me the number of people waiting in line to purchase tickets. Okay, it's not the rate given to me, but it's modeled by a twice differentiable function, L for 0 to 9. Values of L of t at various times are shown in the table above. So these are the number of people waiting in line. Use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30 p.m. when my time was 5.5. Show the computations that lead to your answer. Indicate units of measure. Okay, so again, we're not given a function, so I can't find the exact instantaneous rate of change, the exact derivative. So to estimate 5.5, I'm just going to have to use these two right here. All right, so we should show the calculus that L prime of 5.5, because we're finding the rate, this will be the derivative, is approximately, we're going to do L of 7 minus L of 4, all over 7 minus 4. Okay, again, you need to pull the values from the table here, 150 minus 126, all over 7 minus 4. Now, you have your calculator for these, but again, you can still leave your answer like that if you want to. So this would be 8 people per hour. Okay. That was our 2 points. 1 point for having the right estimate, 1 point for having the right units. So even if you got the number wrong, if you got the units right, you could still get half credit there. All right. B says, use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that the tickets went on sale. Okay, so average, I want to do 1 over 4 minus 0, and then the definite integral from 0 to 4. L of t dt. So again, I'm not given an equation for L of t, so they want me to use a trapezoidal sum to approximate this, using 4 trapezoids from 0 to 4. So here we got 1, 2, 1 for the widths of those trapezoids. Okay. So 1 over 4 minus 0 is obviously 1/4. Here's my trapezoidal sum. I like to bring the 1/2 out in front. So you have 1/2. You could bring it out in front too with the 1/4 if you want to, but I kind of like showing it this way, that this is going to be my trapezoid. All right, so for each trapezoid, think of how you find the area of a trapezoid. You take 1/2 times the height times the sum of the bases. So the height here, and my sum of the bases. Okay, next one has a height, if you will, of 2, sum of those bases. Third trapezoid, 1. Okay. All of that gives me 155.25 people is the average. Okay, part C is the one that's kind of confusing that I want to go over together. And there's a couple different ways you could do it. You could use like a couple theorems. I'm just going to kind of like logic my way through it, and that's an acceptable one as well. I better double check, like even on the calculator portion, that you can do your answer like that. I know you obviously can on the non-calculator, but I better double check that you could also do that for the calculator. Yes, sir?
Does it matter if it's in decimal or fraction form?
No.
Okay.
That wouldn't matter. Okay, part C. So it says, from these first 9 hours, from 0 to 9, what is the fewest number of times at which the derivative must equal 0? Give a reason for your answer. Okay, so if we're thinking about when the derivative is 0, if I were to kind of like graph this, we're just going to have to look, so a number of people in line and when it's going up, and if there's any like horizontal tangents. So basically like if there's any kind of like local mins or maxes. So the way I kind of thought of this is here, remember this is giving you the amount of people. I was like, okay, my amount of people is like increasing until I get to 3 hours after noon. And then all of a sudden I'm like, okay, between the hour 3 and 4, now it's going down. So obviously at some point, there'd be a horizontal tangent there, aka that's when my derivative equals 0. And then it goes back up again. So I'm like, okay, maybe there would be a little min there. So I'm kind of just sketching the graph of the actual like original function. And then it goes back down, down. So the fewest number of times would be 1, 2, 3. Could it have more in between? Maybe. We don't know for sure, but based on the information we're given, the fewest numbers of time at which the derivative is 0, or think like a horizontal tangent, would be anytime there's like a local min or a max. So you can explain this if you look at the guidelines. You can explain it using the mean value theorem and the intermediate value theorem, or another accepted answer, which is basically explaining like what I just said in words. So first of all, we should state that there are no like breaks in our graph, meaning we know this is continuous. Do you guys know how I know it's continuous? It's actually in this statement right here. If it's differentiable, it means it's continuous. Remember that? Differentiability implies continuity. Okay, so here's just kind of how I explained it like in math language. Since L of 3 is greater than L of 1, and L of 3 is greater than L of 4, there is a maximum somewhere from 1 to 4. Okay, that's how, I mean, you could also like literally write that out in words, but I think it's easier to math notate it. All right, similarly, actually, I'm just gonna like write it out again. L of 3 is greater than L of 4, and L of 7 is greater than L of 4. So there is a minimum somewhere in that interval. I should be writing my intervals like this. Either is fine. You can write it either notation. I just see this more often. Okay, and then the last one's same thing. L of 4 is less than, or let's say L of 7 is greater than, I'll keep my L of 7 is greater than L of 4, and L of 7 is greater than L of 8. So there is a maximum on 4 to 8. All right. So we should state that we think at least 3. Okay. Last one is just a calculator one, so let's finish this up quickly. The rate at which tickets were sold is modeled by this function. Okay, give it a new function here. Tickets per hour, that's the rate at which the tickets were sold. Based on this model, how many tickets were sold by 3 p.m.? If I wanted to know the amount, what would I do with that rate?
Insert the t equals 3 into the equation to figure out how many tickets there were.
This is the rate. That would tell me the rate at which they're being sold. I want to know the amount of tickets. Integrate. Yep, integrate. We can do this right in our calculator. So all you would have to show for part D, from 0 to 3, r of t dt, and it says round to the nearest whole number. So let's do that quick. I'm going to type it into my y1s because I make less mistakes that way. So I have 550 x e to the negative x divided by 2. 550x e to the negative. Good. Math 9. 0 to 3. Y1 with respect to x. 973 gets rounded to the nearest whole number. 2 points for that. 1 point for the integral, 1 point for the answer. So here's a good example. If you were to get stuck on part C, don't just sit there. Try part D. That was just an easy plug and shove. Okay, important. Integral of rate gives us amount. Okay, so you only have one left to finish up. Tomorrow the quiz is just on FRQ Type. We'll do it in class 3. Type 3. This short little quiz will be Monday. So just have the Type 3 packet done for class on Friday.